There is a multi-step process to solving hypothesis tests. In this presentation, we will focus on the test for the mean of one population when the standard deviation of the population is known. First, let's discuss the steps to the hypothesis test. The first step is to write the null and alternative hypotheses. The alternative hypothesis depends on the type of test, whether it be the two-tailed, left-tailed, or right-tailed test. Next, state the significance level, denoted by alpha, which represents the probability of rejecting the null hypothesis when it is really true. Once you have this information noted, use the sample data to compute the test statistic. Step 4 depends on what approach you want to use for the test. You may choose to compare the critical value to the test statistic or use the test statistic to get a p-value that you will compare to the significance level. Once the comparison is made, then determine what to do with the hypothesis. You can either reject the null hypothesis or fail to reject it. Let's use these steps to solve an example problem. A swimmer believes that his average time swimming one 100-meter lap is 60 seconds or less. His coach is skeptical of this claim, so he times the swimmer swimming laps. The coach times 10 laps and calculates a mean of 61.5 seconds with a standard deviation of 2.52 seconds. Do the data support the coach's claim that the swimmer's lap time is not 60 seconds or less at a significance level of 0.05? The first step is to construct the hypotheses. The null hypothesis is always a statement that the mean has a particular value. In this case, the null hypothesis is that the mean equals 60 seconds. To test the coach's claim, we use the alternative hypothesis that the mean is greater than 60 seconds. So, this is a right-tailed test. Next, we state the significance value of alpha. The problem asks for a 0.05 level of significance. So, the alpha is 0.05. Now, we need to calculate the test statistic. For a simple mean where the population standard deviation is known, the test statistic is a z-score calculated with the formula. This is the sample mean x bar minus the hypothesized population mean mu, all divided by the population standard deviation sigma divided by the square root of the sample size n. To calculate this statistic, identify the values of x bar, mu, sigma, and n from the given information. The sample mean is x bar equals 61.5. The assumed population mean is 60 from the null hypothesis. The population standard deviation is given, so sigma equals 2.52, and the sample size is given, so n equals 10. Substitute the values in the formula for the test statistic and evaluate to get a z-score of approximately 2.11. For the next step, we have two different methods. First, we will discuss using the p-value approach. Since this is a right-tailed test, the p-value is the probability of a standard normal variable being greater than 2.11. Most technology and tables give methods for finding the probability for values to the left of a z-score. So, using the complement, this is the same as 1 minus the probability that z is less than 2.11. Using either a standard normal table or technology gives a p-value of 0.0179 for a right-tailed test with z equal to 2.11. The next step is to determine whether or not to reject the null hypothesis. We can see that the p-value is less than the significance level, which means the null hypothesis should be rejected. We could also use the critical value approach. Since this is a right-tailed test, the rejection region is all z-scores greater than the critical value. The critical value can be found using technology or a table. The z-score with a right-tailed area of 0.05 is 1.96. Then, we determine whether or not to reject the null hypothesis. we can see that the test statistic is greater than the critical value, which means it is in the rejection region and the null hypothesis should be rejected. So, both of the methods give the same conclusion. We should reject the null hypothesis. Now we need to state that conclusion in the terms of the original situation. The null hypothesis is that the swimmer's mean lap time is 60 seconds, and the alternative is that the swimmer's mean lap time is greater than 60 seconds. Since we rejected the null hypothesis, we conclude that the coach's data provides enough evidence to support the alternative hypothesis. Therefore, we conclude that the swimmer's mean lap time is greater than 60 seconds.